Good morning one and all. In today's lecture we are going to discuss about the parsing. So first of all you have to know what is parsing. So parsing is the second phase of a compiler. So as we know that there are 6 phases of compiler: lexical analysis, syntax analysis, semantic, intermediate code generation and code optimization, and finally code generation. So the first phase takes the source program as input and gives you the tokens, and these tokens will go as our input to the second phase, that is our syntax analysis or parsing phase. So this parsing phase, it will construct a parse tree from the tokens. So with the help of the grammar, it takes the input as tokens and constructs the parse tree. So based on the method we construct the parse tree, you have two different strategies for parsing: top down parsing and bottom up parsing. So the name has given like top down parsing. For example, you consider this grammar: E derives E plus E, E star E, ID. So these are the alternatives. One alternative is E plus E, other one is E star E, and next one is ID. Suppose if you have a string ID plus ID star ID. So the question is, you have to derive the string from this grammar. I can derive in both the methods and explain you what it is. So first, in top down parsing, we will be starting with your start symbol of the grammar. The start symbol of grammar is E. So I start with the start symbol and try to derive the string from it. So this is about top down parsing. So you can say like root to leaves, that is starts from the root of your parse tree and derives to the leaves, or you can say from start symbol to the leaves. So E derives E plus E. So I can replace, so top down parsing follows leftmost derivation. So what is leftmost derivation? Leftmost derivation is when you start replacing the leftmost non-terminal, then it is leftmost derivation. So bottom up parsing follows the RMD, that is rightmost derivation. It starts reverse of rightmost derivation. Rightmost derivation is you start replacing the non-terminal from the rightmost end. So now for this grammar I am going to use leftmost derivation with the help of top down parsing. So this E can be replaced by ID. So I start replacing this with ID, then you have E. Now this is a terminal, you can't replace. Now this is a leftmost non-terminal, then you replace this with ID plus E can be replaced with, since you have an expression ID star ID, this has to be replaced by the alternative E star E. Then this ID, this E can be replaced with ID, then E. Then finally you get E star ID. You have derived the string ID plus ID star ID. So this is, you have started with the start symbol of the grammar and you have derived the input string. So this is the top down parsing. So in bottom up parsing, the reverse case follows, that is, you have a string, you have your string ID plus ID star ID and try to reduce to the start symbol. So if you cannot reach the start symbol, then it is said that the string cannot be passed by the particular parsing or grammar. Grammar will not accept this string. Okay. So now we are going to discuss about the predictive parser in this lecture. So predictive parser is a kind of top down parsing. So in top down parsing itself, we have two variants: recursive descent parser and other one is LL of 1 or predictive parser. So in recursive descent parser, so recursive, as the name itself says, recursive, you are going to recursively invoke a procedure. So until all the non-terminals in your grammar are expanded, okay, until the non-terminals in the production is expanded, you are going to recursively call that functions. So this is recursive descent. So here it involves backtracking. So to understand backtracking, I can have an example here. You have a grammar like S tends to C A D. S derives C A D and A derives small a b and a, right? So and you need to derive a string. You need to check whether the string C A D, you need to check whether the string C A D is accepted by this grammar or not, right? So I start with the, whenever you construct a parse tree in top down parsing, you have to start with the start symbol of the grammar. So I start with my start symbol. My start symbol is yes. My start symbol is yes. I have to, what is the production for yes? You have small c, capital A, D, no other alternative is there. So I have to go with a single option, small c, capital A and D. So here you start, when you see this, it's a terminal, you can't expand. and here D is also, you cannot expand it. So for A is a non-terminal, you are having the two alternatives A, B or A. So among these two options you are able to choose any one. So first what I think is this will lead to my correct result, and I choose this option alternative as A derives A, B. Now further there are no more non-terminals to be expanded. So when you see the yield of my parse tree, you get C, A, B, D. So when you see the string, it does not match, that is which is not equivalent to our required string. So our option is wrong. So our option, that is the method, the one you have chosen is wrong. So among this alternative I have to go for the other one. So since it allows backtracking, the last step alone is backtrack to the previous one. That is I have expanded, at the end I have expanded A with the alternative A, B. So I just backtrack to the previous step. I go back to this A and check for the alternative. The other alternative is A. So I am choosing this A as the production for A, capital A. Now you check the yield of the parse tree, you are able to get CAD. You can derive the CAD. So this is what backtracking says. So if you are gone with the wrong alternative, you can backtrack to the previous step and then choose the other alternative, right? So here you have an limitation, that is if suppose you have many alternatives are there for a non-terminal, then the time needed for this backtracking increases. So the overhead of backtracking will increase here. So that is the limitation of this recursive design parser. Then so in order to eliminate all the drawbacks of this recursive design parser, we are going for the other alternative of top-down parsing method, that is predictive parser. So predictive parser, you can also call it as LL of 1. So why we are calling it as LL of 1 is, so LL of 1, why we are calling it as LL of 1 is, so this first L says that left to right scanning of input. So always we will be scanning the input from left to right. So the first L says that scanning, so scanning of input from left to right. Then this L stays, the second L says that the method you derive, so this is your leftmost derivation. As we said, top down parsing follows leftmost derivation, so this L stands for leftmost derivation, and this 1 inside the bracket, this says that look ahead symbol, that is you can say this way, this 1 says, it describes how many input symbols you use to take a decision, how many input symbols used to take a decision. So here in predictive parser we make use of one input symbol to make a decision, that is whether to pop inside or pop or push into the stack. Okay. Then predictive parser is a kind of top down parser. Predictive parser is a kind of top down parser which involves no backtracking. So in recursive design we told that there is a backtracking, so due to that you have overhead. So in predictive parser, to avoid this backtracking overhead, you are using no backtracking. There is no backtracking in the predictive parser. So when there is no backtracking, of this, then what should you do is, at the beginning itself, right choice must be made, that is whether to choose this alternative or this alternative. So you have to take a decision correctly at the beginning itself. So to this backtracking, to get a proper alternative of the multiple choices, you need to eliminate left factoring. So why should we eliminate this left factoring? Why should we eliminate this left factoring is, suppose see here, this production has two alternatives. In both the alternatives you have a common prefix, A. So I am in a confusion whether to choose the first one or last one. So see here it is 2, so no problem. Suppose you have lot of alternatives like this, all the alternatives are beginning with a common prefix A. So in such a case you are in a confusion to choose the correct alternative. So in order to remove this confusion, you eliminate left factoring from your grammar. So whenever the grammar is given, first thing is you have to eliminate the left factoring. Then the other one you have to eliminate is left recursion. So what is this left recursion, or why should we eliminate this left recursion is, so consider this, if your grammar is like this, if your grammar, one of the production in my grammar is like this, A derives A alpha slash beta. So this alpha beta is capital A, whenever in a rule a capital letter is given, that is at a non-terminal is given, it is a single non-terminal, right? And what is this alpha, beta? Alpha and beta can be anything. It can be a single terminal, or it can be a single non-terminal, or it can be combination of terminal, non-terminal, 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 or even it can be epsilon. So any combination, alpha, beta can be any combination, or even it can be an epsilon, right? So, but whatever it is given in capital letters, that is a single non-terminal, should be marked, okay? And so if your production is like this, so how recursion, we say recursive is repeatedly calls by itself. See this production, A derives A. Suppose when you try to construct a tree for it, right, you have A derives what? A alpha. A derives A alpha, and repeatedly I can define this A with the alternative A alpha. Again I try to define this A with A alpha. Like this it goes on. So this leads to infinite loop. So this leads to infinite loop. This type of production will lead to infinite loop. So you should not have infinite loop in your grammar productions. To avoid this infinite loop, you have to eliminate the left recursion in your grammar. So for that, what is the rule? So if you have a production of this format, A derives A alpha slash beta, then this has to be transformed like this. That is, A derives beta A dash. So A dash is our new term, right? So to eliminate our left recursion, you are forming such production. One production is equivalent to, I am changing this to two different productions, that is not having recursion, right? A derives this beta, introduce a new term A dash, and A dash derives, take this alpha, and A dash followed by epsilon. So this is the rule for eliminating left recursion. Rule for eliminating left recursion. Whenever a production has left recursion, that production has to be transformed into this format, okay? This is left recursion. Like that, you have a rule for left factoring. You have a rule for left. So left factoring, as I told you, left factoring is you have common terms. You have common terms in all your alternatives. So you have a production A alpha beta 1 slash alpha beta 2 alpha beta 3. Like this it goes on till alpha beta n. If your production is of this format, that is, you are having common terms in my alternatives. You are having alternate productions. In the alternate productions, you have common terms that is given as alpha. As I have already told you, alpha is alpha beta, can be any combination. It can be a terminal, non-terminal, or even it can be epsilon. But whatever which is given in capital letter, that should be a single non-terminal, right? So if your production is of this format, you have to transform in such a way that there is no factoring, there is no such choices are available. So why should we eliminate this left factoring? Because you get a confusion among the many choices which one to choose. That at that point you will get a confusion. To remove that confusion only, you are going to eliminate this left factoring. So what I will do is, I will start rewriting this grammar into two different productions. A derives, take this common term is alpha. So write this alpha first, then introduce a new term A dash, then A dash derives. So what is the remaining? We have left out in this production. Alpha we have included, the left out is beta 1, beta 2. So make all these alternatives in the A dash, beta 1, beta 2, beta 3, like this it goes on up to beta n. So this is the rule for eliminating left factoring. So we have discussed the rule for left recursion, we have discussed the rule for left factoring. So whenever you want to parse anything, whenever you want to parse a grammar using this predictive parsing method, the first step is you have to eliminate the left recursion, eliminate left factoring. Only after that you can apply the predictive parsing method, okay? So as of now we have understood what is top down parsing, bottom up parsing, and what is the recursive design parser and what is predictive parser, and what is the prerequisite for predictive parser. You have to eliminate left recursion, eliminate left factoring, right. So now we go through the steps for parsing in predictive parser. So for predictive parsing, you are going to predictive parsing steps, or for LL1 you are writing the steps. So our first step is you have to eliminate left recursion and left factoring. That is our first requirement. And step 2 is you have to find out the first position of all terminals and non-terminals. You have to compute the first position for all terminals and non-terminals. And third one is you have to compute the follow of non-terminals. There is no follow for terminals, follow is only for non-terminals. Okay. And fourth step is you have to construct the parsing. You have to construct the parsing table. And fifth step is you check your grammar by taking a sample input string, and so give the step name as parse the input string. Okay, these are the steps to be followed in order to parse a grammar with predictive parsing, right. So I have told you the rules for left recursion and left factoring. Okay, first whenever a grammar is given for you, you have to check for left recursion, left factoring. If there is no left recursion, left factoring, then go for step number 2. If there is something like recursion or factoring, you eliminate it and go for the next one. So now what is this first of terminal, non-terminal? So first I will give you the rules and then we can go with the sum. So first of terminal and non-terminal. So what is the rule for this one is, I will give you first, whenever you want to find the first position, so first of a terminal, first of terminal is always a terminal. Include the terminal in your first. Then if you have a production like this, x derives epsilon, then in first of x include epsilon. And third, if you have a production of the format x derives a, then in first of x you include this a. Suppose if you have a production like this, x derives x1, x2 and so on, then in first of x you have to again compute this first of x1. So these are the 4 rules to be followed in the first. So first of terminal will always a terminal. When there is a non-terminal and you have a production like this, x derives epsilon, then epsilon should be included in the first of x. If you have a production like x derives a, then first of x will contain terminal a. If your production is having only non-terminals, x derives x1, x2 like this, then first of x is equal to first of x1. So these are the rules to be used for computing the first position. And second one is follow. So how to compute this follow? So follow is this, you will be computing the follow position of a non-terminal. So who is following that particular non-terminal, that I have to find. For this you have 3 rules. So for follow you have 3 rules. First one is whenever you have the start symbol, follow of the start symbol, follow of start symbol, that should be dollar. You have to include dollar in the follow of start symbol. That is our first rule. And second rule is, if you have a production of the format a derives alpha, b beta, provided beta is not equal to epsilon, which means you are having something in place of beta. In such a case, you will be finding this follow of b. Now who is following B? Who is following B? It is beta. So beta can be anything. Beta can be a terminal, or it can be non-terminal, or it can be combination of anything. So in that case, I will be computing this follow of B. So who is following B? Beta. So if someone is there, then I have to find the first position of that someone. So I will give here, it is first of beta. Follow of B, someone is following B. Who is that? Beta. For that beta, I find the first. That will be in follow of B. This is the rule. And third rule enna appadina, that is A derives alpha B beta, and this beta, sorry, alpha B, beta is nowhere. There is no beta in the given production, or even this beta can be epsilon. If suppose beta is epsilon, it is understood that there is no one following this B. So if your production is of the format A derives alpha B, then no one is here, so I have to go for the left hand side. So follow of B is given as follow of A. Follow of B is follow of A. So in follow you have three rules. Follow of start symbol, you have to include dollar, and the remaining two rules is given based on the format of your production. If you have alpha, B, beta, then beta is not equal to epsilon. Someone is there, then I have to find the first of beta and place them in follow of B, or else there is no beta here, only B is there. So when you find follow of B, you have to find follow of A. Follow of B equal to follow of A. This is the three rules. For every production, you have to apply these three rules for finding the follow of all non-terminals. Okay, so this is your follow. And next is parsing table. So table, as you have a table, you will be having a table format which contains your, you will be having a table format in which the rows will be your non-terminals. Rows will be your, all here will be non-terminals, and here you will be placing all your terminals and dollar symbol and the column wise, right? So now how to make entry in this parsing table is based on every production. So you have to take every production and find, for example, you have a production like this, S tends to small a, then which means that, see, this is the production. For this production, I have to make an entry in the table. So this production should be placed where? I have to find where should we place this production in the table. For that, S derives A. So see the first place, see the first place of the production, see the first place of the right hand side. So here, if you have a terminal, then for the respective, see here, for if it is the terminal, then table entry of this non-terminal comma terminal, at that place I have to place the production S derives A. So in my table entry for the non-terminal S with related to this small that is terminal A, you have to place the production S derives A. This is one format, that is S derives A. If suppose you have a capital letter, that is non-terminal. So in such a case, what should we do is, see the first place, you are not having terminal. So I can find the first place, first of capital C. Already we have found the first. So you see the first of this capital C. So in first place of capital C, what do you have? So if suppose you have a production C derives, capital C derives small d, you are having another terminal D, then first of C will be small d. So yes, for this table entry S comma capital C, you have to make an entry C derives D. You have to make an entry C derives D. So like this will be going on. You check for the first one. If you have A, make an entry like this. If you have a capital letter, find the first place and then then make a table entry, right? This is about constructing the parsing table. And the last step is parsing the input string. For parsing the input stream, here you have an algorithm like this. So you have a parsing algorithm. So this parsing algorithm there is parsing program or parsing algorithm, you can say. Here you have a parsing table that we have constructed for a particular grammar, and this side you will be having a stack. You have a stack, and here you have your input buffer. here you have a input buffer. Initially, see, initially the stack will be having dollar at the bottom of the stack and input buffer end is marked with dollar. So this dollar indicates the end of stack and end of input buffer. So initially what we do is, whatever string you need to process, that should be placed in the input buffer. For example, I have a string like A plus B. So you have everything will be separate, A plus B, and to denote the end you have a dollar. At the beginning it points, the pointer will point to the first place of my input buffer, right? So in stack you will be having the stack symbol. So on top of stack you will be having the start symbol. On top of stack only start symbol is available. So if suppose my top of stack or the starting symbol of my grammar is X, starting symbol of my grammar is X, so it is in the top position. So program will point to the top of stack. This is your top of stack. And how it works? So initially you will be having your input string in the buffer and top of stack will be having the starting symbol of my grammar, right? So now you have to for every input symbol and check for the entry in parsing program will check with the top of stack and find a match in the parsing table, right? So if this X, so with this we have some points. So if and top of stack you have A, in top of stack X, instead of this X if you have A, right? So both the top of stack and the input pointed symbol matches, so you have to pop. So if X is equal to A, which means the top of stack and the input buffer is same, at this point you have to pop that symbol out of the stack, pop the symbol out of the stack, and the input pointer will be advanced to the next symbol. Okay, since it is understood, it is available, you can parse through the grammar, you have to pop it out, right? So if suppose you are having a capital letter, that is you are having a non-terminal. So you have non-terminal, then here you have A and you have to find the respective match in the parsing table. So for this capital X and for small a, what is the table entry? So if you have to take this table entry X comma A. So for this table you have table X comma A, what is the production available in the table? So you may have some productions here, that production should be pushed onto the top of the stack, pushed onto the top of the stack in the reverse way from the right end to the left, that will be pushed onto the stack, right? Then after that again you start continuing whether both the symbols are same. When both the symbols, that is the symbol in the input buffer and top of stack is same, you have to pop it out, or else if you have a non-terminal here, then I have to check with the table entry what production I have it and then push it onto the stack. Like this I have to continue. So if suppose if there is a situation you does not have any entry in the table for this non-terminal and terminal, you are not having an entry in the table, then you can say that the string cannot be passed in the particular grammar. Okay, that is how the input parsing will happen, right? So now we can see a example program or example problem, how it works. So I have a problem. S tends to, S derives capital C, capital C, capital C derives small c, capital C or D. This is my problem. This is my problem. So you have to parse, you have to use LL of 1 parsing and find out the string whether C, D, D is accepted by this grammar or not. This is my question. So first, what is my first step? I have to eliminate. So what is our step 1? Step 1 is eliminate left recursion and left factoring. So you check for left recursion. So what we said recursion? Recursion in the sense the left hand side of your production, right hand side of your production la first symbol. If both are same, then there is left recursion. Check for the first production, you are having S here and C. So it is not same, so no recursion. Here also there is no recursion. So it is understood in our given problem there is no recursion, there is no left recursion. And what about the factoring? So factoring is you have common prefixes in most of the alternatives. So here there is no alternative, and check for this production. So you have two alternative, that too you are having different prefixes, so there is no left factoring. No left recursion and no left factoring. And step 2. Step 2 is you have to find the first position for all terminals and non-terminals. So first we have to classify what are the terminals and non-terminals in my problem. So what are my terminals in my problem? Small c and capital D. Small c and capital D are my terminals, and about non-terminals, in my given grammar, capital S, comma, capital C. These two are non-terminals, right? This is capital C, right? So now, as we said, what is our first rule? First position for all terminal is terminal itself. So write it. So first of small c is small c, then first of small d is small d, and for capital S, first of non-terminals. So first of capital S. Check the production. Who is in the first place of C? Who is in the first place of C? You are having a capital letter. So what should you do? You have to find the first of this capital letter. So you have to first of capital C. Who is first of capital C? First of capital C is, see the first place of the capital C production, you are having small c, small d. So there are two alternative productions. Either it can be C derives small c capital C, or it can be C derives small d, right? So there are two possibilities. Both are having terminals at the beginning. So these two must be included in the first position of this capital C. So first position of capital C is small c, comma, small d. Again, when I find the first position for capital S, that is equivalent to the first position of capital C, which is small c, comma, small d. So first position of S equivalent to first position of capital C, which is equivalent to C and D. So we have found the first position. So rules are clear here. If you have first of terminal, it is always a terminal. First of, suppose if you have epsilon, then that should be included in the first position of X. If it is A, then first position of X is equal to A. If suppose you have a capital letter, you have to find the first position of this capital letter and add to the first of X. So by using the rules, we have found the first position. So next is you have to find the follow position. So for finding the follow position, just erase it. So we will have rules alone for constructing it. Step 3 is I have to find the follow for all your non-terminals. So what are our non-terminals in my grammar is capital S and capital C. So we have to take, I told you have to take every production and apply the 3 rules. So I will take the first production. So what is my first production? S derives capital C, right? So I apply rule 1. What is my rule 1? Rule 1 is applicable only for the start symbol. Rule 1 is applicable only for the start symbol. So what is my start symbol? S. So I write follow of capital S is $. Follow of capital S is $. Then what about rule 2? Rule 2 is you have a production of the format A derives alpha, B, beta. Beta is not equal to epsilon. That is, someone is following this B. Then in that case you find first of beta. So now you have this production. I make this A. So you have to relate this formula with the format here. So A, this S can be taken as A, and for rule 2 beta must be there, right? So I can make this position as alpha, which is meant to be epsilon, right? And this capital C is taken as capital B, and this is taken as beta. So I have told you alpha, beta can even be epsilon. So with that I am assuming this place to be alpha, epsilon, and this is capital B and this is beta, right? So with this second rule, what is my rule? Follow of B equal to first of beta. Who is B here? It is capital C. So I have to write like this: follow of capital C equal to, who is beta here? Again capital C. So you write first of beta. Who is beta? Capital C. So what is capital C's first first of capital C already we have found out, that is small c comma d. So C comma D. So follow of C is C comma D. Okay, by applying this rule 3, what is our rule 3? Rule 3 is beta is no more. So there is no more beta. So in my production S derives capital C, I want to assume this as A, and here it is clearly understood there is no beta. So I make this as alpha and this as B. There is no beta, right? So if there is no beta, what is my rule? Follow of B equal to follow of A. If no one is following B, then you have to go for the other side. So follow. So follow of, with that, how to write is follow of capital C equal to follow of S. So who is follow of S? Follow of S is already found as dollar. So in follow of C you have to include dollar. Already in follow of C you are having CD. Here along with the CD one more terminal is added. Follow of C is dollar, right? So now we have completed 3 rules, right? So once you complete all these 3 rules for a production, first you have to summarize like this, or what all you have found in this production. Follow of S is dollar and follow of capital C is, so here you have found it is C comma D, and in this third rule you have found follow of C, dollar will also be added, right? Follow of C you have follow C D dollar, right? So now first production is over. Come for the, this is first production, come for the second production. Second production you have C derives small c capital C or D, right? So take this and you apply the rule. So rule number 1, so rule 1 is applicable only for the start symbol. So since it is not the start symbol, rule 1 is not applicable. Rule 1 is not applicable. For rule 2, you have C derives small c capital C. Take this as A alpha, sorry, you can alpha B beta, whether it is right. We cannot do it so, because this B must be a single capital letter. So here I cannot make this. So rule 2 is also not applicable. So only rule 3 is applicable, because this is taken as A, this is alpha, this is B. Beta is no more. So there is no beta. So how to compute the follow of B? Follow of B equal to follow of A. So B is, you are having capital C, and in A place also you have capital C. So follow of C is equal to follow of C, no meaning. So follow of C is C D dollar, right? So this is what you have, and yes. Now step number 3. Step 1 you have found out no left recursion, no left factoring, and step 2 you have found out the first position, and step 3 you have found the follow position of follow of C and follow of S. So in follow of S, okay, now you go for the step number 3 or step 4. 1, 2, yeah, step 4. Step 4 is construction of parse table. Step 4 is construction of parse table. So in construction of parsing table, you have to make an entry of all your non-terminals here and your terminals C, D, dollar, right? Then how to make an entry in the table. So take the first production. So what is my grammar here? S derives C, C. So S derives capital C. So when I have capital C here, I have to compute the first of this capital C. Who is first of capital C? First of capital C is C comma D. So in place of this small c and small d, you have to place the production S derives capital C, S derives capital C, C. Can you understand how we have done this? S derives capital C. So in the first place of S, you have capital C. So for that capital C, we have found the first position. In that first position, you have placed the productions. Okay. Then next step. So this is over, and come for the second production. C derives small c, capital C. So who is in the first place of capital C? It is small c. So you relate with this capital C and small c and write the production C derives small c capital C, small c capital C. And the next one C, the other alternative is D. In the first place you are having a terminal. So C with related to D, you write the production C D. Okay, this is how you make an entry in the table. So for this, that's all. That is, you have constructed the parse table. So S derives CC, and here C will be the first place. So I make an entry in the capital C small c, C capital C, and for the small c you make an entry C derives small c capital C, and for this D you have make an entry. And step 5 is parsing. So what is the string we have given? C, D, D. You need to parse the string. So I write the parsing here. Step 5, parsing the input. So for parsing you have a stack and input, and here you describe the step, right? So initially, what is the, in stack you will be having dollar, and in top of stack you will be having the start symbol, sorry, the start symbol is capital S for my grammar. And what is my input given? C, D, D dollar. I have to find whether the string is accepted by this grammar. So initially my input buffer is loaded with the input string that end with dollar, right? So this is my initial step. And next step is, so you relate, see, on top of stack S is there, on the input pointer is pointing to the first input symbol, it is small c. So I will find the relation between the capital S and small c in my table. So for capital S and small c you have a entry S derives capital C capital C. So this has to be pushed into the stack from right to left. So what you will have is, you will have C, C, and here you have the same C, D, D dollar. How have you done this? With the production S derives capital C, right? So now again you check the first top of stack and the first input symbol. Top of stack you have capital C and you have small c here. See the relation in the table, capital C for small c, the relation is C derives small c capital C. So what I told you, you have to push it into the stack from right to left. So C will be going in first. So already you have the capital C, and for this capital C I am going to push capital C, then small c. Then input symbol you have the same as such, since you have not found a match till now, right? See here now, top of stack you have small c, on the input pointer is pointing to small c. So both the symbols matches. So I told you in stack, if you have same input symbol in the top of stack and the input, then that will be popped out of the stack. So it will be popped out of the stack, and you have the remaining. What will be remaining here? We will be having capital C, here you have small d dollar, right? So then you find the relation between this capital C and D. So this capital C and D. So what is the relation between capital C and D? You have an entry C derives small d. So instead of that capital C, I will be placing the small d, and you have D dollar. Now your top of stack and input is same. So if both are same, I will be popping that input symbol out of the stack, and you have the remaining. What you have remaining is only one capital C and one small d is left out. So what is the relation between top of stack? That is, top of stack is capital C and input is small d. Relation between capital C and D is C derives small d. So I have to replace this capital C by D, and in input you have D dollar. Now your top of stack and the input are same, so you have to pop the symbol out of the stack. So that will be popped. After popping this D, you will be having dollar here, you will be having dollar here, and finally, so what is the case in the parsing is, so if both the input symbol, top of stack and input symbol matches, then you have to pop. If it doesn't match, you are having only a non-terminal, then find a proper entry in the table and push that onto the stack. If suppose you are having dollar at the stack and dollar at the input symbol, that denotes the end of parsing. So you have to say the string is accepted. The string is accepted. So now we have passed the grammar using predictive parsing, and we have checked whether the string is accepted by this grammar or not. So I give a summary of what we have discussed. Top down parsing. So in top down parsing we have discussed how to solve a problem in predictive parsing method. So in order to solve a problem in predictive parsing, you have to eliminate the left recursion and left factoring first, and then you have to find the first position, follow position, and then you construct a parse table, and then you can take any input string and check whether your grammar is parsing that input string or not. Thank you.